take it away.
Thanks, Tom, for the introduction. Yeah, I'm quite excited to be here virtually, I guess virtually in Boulder this week. I was asked to talk about the topic of quantum gravity in the lab, and I'll say right away that I find this slightly intimidating because I know a fair amount about labs, but less about quantum gravity. It's something I'm fascinated by, but certainly not the expert on. So my goal will be, though, to sort of give you an experimentalist's perspective on sort of what are some of the things that we can measure to try to connect to some really kind of exciting theoretical questions and developments. So I thought I would start by giving you all just like a peek into my lab. My research group does experiments with laser-cooled atoms. So you can see there's a fairly sort of complicated setup that needs to be built up to even start to do these experiments. Here, this sort of on the right here, you're seeing a cloud of atoms collecting at sort of micro-Kelvin temperatures. We can optically trap them to make some array that looks like this. And at the end of the day, though, we kind of think of these as really sort of model systems for studying quantum mechanics. And one of the things we love is to get to a regime where we have something that looks sort of conceptually simple, but is a sort of a wonderful playground for starting to understand, well, one thing that I'm kind of fascinated by is trying to understand entanglement in quantum systems. And this is something that I originally got into from the perspective of asking kind of how can we make useful entangled states. So for example, there are certain forms of entanglement that are useful maybe in computation. That's kind of a famous example, also in precision measurements. So here are some kind of sketches of quantum states known as squeeze states, which are collections of spins where the fluctuations in some particular quadrature are reduced in such a way that the quantum noise is reduced in such a way that you can do a better precision measurement of perhaps time or magnetic fields. So these are types of entangled states that one can make in the lab with laser-cooled atoms. And I drew the pictures I've showed you the pictures on the left here, partly to kind of illustrate that sort of one area of interest are states that are entangled, but in some sense conceptually simple, right? The fact that, so one can demonstrably show one has, let's say, thousands of atoms entangled, but I've shown you a picture of the quantum state, and generically, you know, a quantum state of thousands of particles is something that you would think is something that's exponentially complex to describe. But there are certain cases where I can draw a simple picture in terms of, let's say, the average magnetization and the fluctuations around it. That's a sort of a very special case. Of course, what's sort of far more common in nature, if I have some interacting quantum system, is that there is entanglement, but it's not in such a simple form, right? So entanglement is in fact very common in interacting quantum systems, but often it's perhaps useless entanglement, or maybe it's not useless, but we don't know how to think about it, right? And so while I would say kind of one area that my toolbox of cold atoms are used for is quantum control, making specific entangled states that we know how to use, another area is what I would call quantum simulation, which is realizing some perhaps conceptually simple form of interaction, but nevertheless the interactions can give rise to complex entangled states that we would like to understand, perhaps because that type of entanglement shows up in the physics of strongly correlated materials, perhaps because if we understood it better, it might be a resource, let's say, for computation. And so this other domain of quantum simulation is kind of how can we understand more generic interacting quantum many-body systems. And one of the things that sort of I've found is that in this quantum control arena, I really depend a lot on being able to visualize things, like visualize these reduced quantum fluctuations. And that kind of raises the question of, you know, are there other ways in situations where one has more complex quantum states of visualizing them? And this is kind of what drew me, sort of attracted my interest in the beautiful kind of idea of holographic duality that I assume you have heard about and thought about over the course of this summer school, which is that in certain cases, if I have some quantum many-body system in, let's say, d spatial dimensions, like this 1D system on the left here, maybe a ring of qubits, in certain cases, there's a mapping to a higher dimensional system with space-time curvature and gravity, where that sort of geometrical picture explains something or gives a way of visualizing something about the structure of quantum correlations in the quantum system, right? So that, to me, is a beautiful idea, that there might be cases where there is a geometrical picture or a simpler picture in terms of gravity for understanding this complex interacting quantum system. So when I sort of learned about that, I was curious, is this something that one can study in experiments? We can build quantum systems and probe them in the lab. Is this concept of sort of an emergent holographic bulk geometry, is that something that one could probe experimentally, either in simple model systems, or in cases where it's not known whether there is such a picture, but perhaps you could discover it by probing the system. And if that's the case, then maybe some sort of conceptually simple models that have known holographic duals could provide a starting point for understanding and visualizing kind of a wider range of quantum many-body systems. So kind of my motivation to some extent is, what can we learn about quantum mechanics from using these ideas from gravity? So if you want to have a starting point, you'd like to have maybe a system that's simple to think about on the gravity side. And my understanding from talking to theorists is that the simplest thing to think about is a black hole, which on the quantum mechanical side is a system that is maximally chaotic, one where information spreads exponentially quickly across all degrees of freedom. So the idea, and in some sense, actually, so there's this conjecture, this fast scrambling conjecture that black holes are the fastest scramblers in nature. And in some sense, actually, I would say this is a sort of a sharp theoretical prediction, right? That there's a fundamental limit on how fast information can become delocalized, spread from one to many in any quantum system. And the idea that there are sort of predictions coming from people thinking about quantum gravity, about really kind of quantum systems that we might build in the lab, was really what kind of kicked off interest in starting to ask, is quantum gravity something that one can study in the lab? And again, the motivation for those of us who spend most of our time thinking about quantum mechanics is in part about, what can we learn about the fundamental limits on quantum dynamics? Can this teach us something about fundamental limits on transport in strongly correlated materials? This process of fast scrambling, how quickly information scrambles, that actually plays a role in asking how quickly one can get to a regime that can't be simulated on a classical computer. So it's related to quantum supremacy tests. There are implications for quantum error correction. So there are lots of reasons, I think, sort of from the quantum mechanics side for being interested in connecting experiments with ideas from quantum gravity. Of course, there's also potentially interest from the side of understanding gravity, right? So this whole idea of fast scrambling is something that was thought about as a way of resolving the black hole information problem. What happens to information that falls into a black hole? No, it's not lost, but it's very quickly becomes difficult to access by any local measurement because it becomes hidden in complex quantum correlations. So that brings me to sort of what are the motivations? Why might you want to study quantum gravity in the lab from the gravity side, right? What might you hope to learn? And this is something where, again, I am not the expert, but some questions that I've heard posed are, for example, is space-time truly smooth, or should we, because of quantum mechanics, think of there being sort of a shortest length scale, the Planck length, and is there perhaps some discretization on that length scale? That's actually a hard thing to probe in experiments, which is why it's to some extent an open question. Is gravity a phenomenon that really truly emerges from entanglement among microscopic quantum mechanical degrees of freedom? Is that really the fundamental way we should be thinking about gravity? So those are a couple of questions that one could ask from the gravity side. One thing I'm actually curious about, though, sort of before I talk more, is what your questions are. So I wanted to kind of start this actually by doing a little bit of a kind of brief breakout discussion and having you report back. So that what I'm curious to learn to get to know all of you a little bit is kind of what are the questions that motivate you, maybe in your research or more broadly. And so what are sort of your questions about gravity and its intersection with quantum mechanics, and also perhaps how you can imagine experiments perhaps helping to address them, okay? So those are two questions that I would like you to discuss in small groups. If possible, let me see whether we can do this. I will put a prompt on Slack on the lectures channel, and it will start a little thread, and you can post some thoughts under that thread. But then also we'll reconvene in a few minutes, and I'll ask a few of you to sort of report out from your breakout group. Sound good? Okay, so I'm going to start a breakout group. We will do this with 5 to 6 people per room so that you all get to talk a bit. Here we go. Okay, so I just put a little thing in the lectures thread, which I hope people can just kind of respond within that thread. I will peek into some of the breakout groups.
Sure, yeah.
Yeah. All right, some people are still in the breakouts. They have 20 seconds to come back. I didn't see anyone answering on Slack, but I'm hoping that's just because you were, so caught up in discussing amongst yourselves, which is also good. Although if you have thoughts, feel free to type them in. But once everyone's back, I will actually ask if there are any volunteers.
Yeah.
Was there?
Did you create a channel in Slack?
Oh, sorry. Maybe this wasn't clear. Okay. So good. So apparently this was not clear. So there's a lectures channel. And for now, what I did was I just put the question into the lectures channel. Okay. And you can respond to the thread. So it looks like at least one person is typing in response to that thread. Maybe going forward, we'll have our own channel for this particular set of lectures. But anyway, okay, so even if you didn't get around to typing, if you're still typing, that's great. But maybe I can get a few volunteers to share some thoughts that came up in your breakouts. Anyone willing to either just like wave and raise your hand or raise your hand on Slack and report back? I certainly heard some good discussions, so.
We had a small confusion, probably more like my own confusion. So we had a discussion about, on the CFT, probably you can do something in the labs to simulate the CFT behavior, but then we have a dual description for that. But then it's not that we're actually creating the bulk. But then there's a sort of a different perspective that is, ER equals to EPR, in that if you collapse two bunch of entangled pairs, each on one side into a black hole, then it somehow creates a wormhole. And in that picture, you have both. You have both the entangled pairs with, it's more like, I don't know, more like a CFT states. And then there's also the wormhole in the same picture. Is there which one is more like the real thing that you can probably produce in the lab? That's the confusion we had.
Yeah, and I think that's a fairly deep question. I think it's pretty clear, though, that sort of on the like CFT side, if there's something where you can like write down a description of a quantum state or a Hamiltonian, then that's something that we're likely to be able to realize in the lab. And maybe there's some way that we can probe to what extent that behaves like a wormhole, right? So yeah, and so that's all kind of relying on this concept of holographic duality, right? I heard some other discussions that were sort of coming from a different perspective about like massive objects in the quantum regime. Does anyone want to comment on that, actually? I think, Peter, did I pronounce your name right? I think you brought this up.
I mentioned this experimental group at Vienna that's trying to put massive objects in quantum superpositions, but try to push the boundary so that the objects are massive enough that you can also detect gravitational effects between them. And they're still some ways away from being able to make the object massive enough so that they can detect gravitational effects, but not so massive that they can still be coherently superimposed. And I think that once they're able to close that gap, that it'll be really interesting to see what comes out of that research. I'm not too familiar with it, though. I can send a link to their website if anybody's interested.
That's great. Feel free to send a link, and that's also something I'll say a bit more about later in the week. So so broadly speaking, the way I see it, there are kind of two classes of approaches maybe to trying to study quantum gravity in the lab. One of them is, can we do precision measurements in a regime where both gravity and quantum mechanics are somehow playing a role? And this is kind of exactly what Peter was just talking about. Can I take a massive object and put it in a quantum superposition state? Or maybe if it's not very massive, but I can still make the superposition macroscopic enough in some way, I can test some theories of, for example, does gravity cause some unexpected collapse of the superposition? So that's sort of one approach, is probing systems where quantum mechanics and gravity both play a role by precision measurements. And then the other approach is the one I kind of alluded to earlier, the approach of simulation. So this was also brought up, like, can I use this ADS CFT duality to build something on the kind of CFT side? I have some quantum system that we think might have a holographic dual that's interesting. It's a black hole or a wormhole. Can we make that in the lab and probe aspects of this duality? And then a third thing that happens on the quantum simulation side is what I might call analog gravity. Can I realize analogs of Hawking radiation, where instead what I have are the radiation is in the form of phonons rather than photons, for example. So these are kind of various directions that are explored in experiments. All of them in some way involve, I would say, kind of quantum engineering, building, having a good control over the quantum system that you build in the lab, either because you need to do a very precise measurement in a regime where quantum mechanics and gravity are both relevant, or because you need to build some designer Hamiltonian that you think might have an interesting holographic dual under this ADS-CFT duality. Because there are so many, so there are a number of different approaches, and there are also a number of different platforms that are being employed, ranging from cold atoms, which is sort of my comfort zone, my toolbox, to trapped ions, superconducting circuits, right? So these are various kind of systems of well-controlled qubits, or also kind of solid-state materials that are believed to have some well-understood holographic dual under ADS-CFT duality. So lots of different approaches being taken. And I think one thing I want to kind of highlight is that actually this topic of quantum gravity in the lab, you might think it's going to be, there's not much to say about it because it's so hard to study quantum gravity in the lab. But that said, it's actually an extremely broad topic in terms of the questions that are being explored and the approaches that are being taken. So I'll warn you, I'm not an expert on all aspects of this, but I will. My goal this week will be to try to kind of give a flavor of questions that are being explored and some of the experimental tools that are being brought to them. But I'm actually going to warm up. Oh, there's a question. I think there's a, Marcus, do you have a question?
Yes. So I was wondering about this quantum gravity in the lab, especially with the, we were talking about the Vienna experiment. I'm assuming we're in a gravitational field. So wouldn't that like we're doing an experiment about gravity in a place where gravity is, I guess, not just some non-zero gravitational field that we're like, let's see here, try and find the word, we're submersed in.
Yes.
Can this like effect be taken into account?
Yeah, so I guess one has to think now about what exactly the experiment is, right? But in general, sort of the types of experiment involve trying to have sort of more and more massive objects in, let's say, more and more macroscopic superposition states, for example. And now the fact that we are in a gravitational field is something that might be some, depending on the experiment, you might actually be using that. But yeah, I think maybe, sorry, I feel that that's a question that might be easier to answer in the context of a very specific experiment. So maybe we can discuss that later in the week when we talk about some of these experiments. Does that make sense?
That makes sense. Thank you.
I think my understanding is that situations where you have quantum objects in superposition in a gravitational field, that has been studied like even decades ago, where you put like, I don't know, 2 photons in a gravitational field, and then you can detect some measurable changes, whether the photons are higher up off the ground, like even by something like 10 centimeters, the change in gravitational field can be detected in that superposition. But what the Vienna group is trying to do that's very novel is they're not just trying to put something in a superposition in a background gravitational field. They're trying to make the thing that's in a superposition creating a gravitational field. So that's much harder because you can no longer just do that with photons or with a couple of atoms. We need something that has some substantial mass to it. And that's why this research is, I think, pretty interesting, because it's previously you had something that I wouldn't really call quantum gravity. It's just quantum system in a gravitational field. Now you can actually maybe call this quantum gravity effect, because the thing that's in a superposition is also sourcing the gravitational field. So I don't know, maybe that partially answers the question.
And I think maybe another comment is in anything that's been done so far, the gravitational field is just like being in an accelerating reference frame. And
yeah,
that's another thing people are testing, actually. Yeah, but exactly. So good. So yeah, Other questions at this point? Okay. So I thought I would start today, as I said, there's lots that we can talk about. I thought I would start today almost by way of kind of also introducing myself, by saying a little bit about work we're doing in my own lab, exploring kind of this concept of how can geometry emerge from quantum correlations. So this concept of emergent geometry, I don't want to disappoint you. I don't have a system in the lab that has some exact holographic dual, but I think you're going to see that we can get at some of these concepts of holographic duality in experiments. Then in the rest of the week, for the first part of the week, I'll be talking more about experiments kind of, again, inspired by holographic duality and this question of, for example, information scrambling. Could one realize systems that are dual to black holes, or systems that are at least fast scramblers of quantum information? And perhaps more specifically, how does one actually measure this process of information scrambling? How does one measure entanglement in the lab, which has a geometrical interpretation under holographic duality? Say a little bit about experiments that have been done using quantum teleportation approaches to measure quantum information scrambling, and this is kind of connected to the idea of decoding Hawking radiation. So those will be kind of the next couple of lectures will be more sort of exploiting the simulation approach. And then towards the end of the week, I'll get more onto the precision measurement side. So this question of, can one study massive objects in a quantum regime and learn something from that? Yeah.
Excuse me. Sorry, are you referencing slides
am I
right
not?
now?
Oh, am I not sharing my screen?
No.
I forgot to reshare at the end of the breakout. Thank you so much for reminding me. Okay, so so now you see it, right? Yeah. Okay.
Yes,
so that's
yes.
the plan for the week. I want to give you a flavor of questions being explored in the experimental tools, and yeah. So now you see it written out. Sorry, it wasn't there while I spoke. Okay. So yeah. So let me spend the rest of the day today with a story about recent experiments in my own group, where I mentioned our sort of toolbox are cold atoms. And we're motivated by this question of, are there situations where one could experimentally probe, or ways one could experimentally probe this idea of a duality between this d-dimensional quantum system and some emergent geometry in one additional spatial dimension. And so this is something I think I first got interested in when I saw some picture like this, of this concept that somehow I have this quantum many-body system, and through this process of sort of trying to sort of renormalize these degrees of freedom to come up with some effective low energy description, right? One goes through kind of a process of coarse graining that gives rise to actually this kind of emergent extra dimension. And it's in that extra dimension that one, in certain cases, might have something that looks like it has space-time curvature and gravity, might look like a black hole, depending what exactly this quantum system is. So what are the experimentally observable consequences? And so, when I first heard about this, the first thing I learned was that one prediction coming from this is that if you could build something that looks like a black hole, it would have this property that quantum information exponentially quickly becomes delocalized across all degrees of freedom. So, my first question was, is this something that you could actually study in the lab? How would you do that? And it seemed hard at first glance to me as a cold atom experimentalist. But why does it seem hard? So let me tell you a little bit about sort of the standard toolbox in my field. In fact, what I'm showing you here, I shouldn't even call this standard. This is sort of state-of-the-art, what's possible in some of the most advanced labs around the world. So one of the nice things about these cold atom experiments is that it has become possible to have really a very, very well-controlled quantum system, where by now in a few groups around the world, it's possible to have even individual atoms that you can sort of position wherever you want. Each of them could encode a quantum bit in two of its internal states. You can detect them at the single particle level. So there's really this combination of kind of a high degree of control, very good detection, and also scalability. And there actually aren't so many systems where one can also have sort of hundreds of quantum bits controlled at the single particle level. So that's kind of the state-of-the-art toolbox of cold atoms. And what I've shown here on the left is saying there's good control over the individual particles, but of course, if we want to study some quantum many-body physics, we also would like to generate some kind of interactions. And there are also tools for generating interactions. So, for example, if one has one thing you can do is trap these atoms in an optical lattice that's formed from a standing wave of light. And if two atoms sit on the same site, they interact with each other. In this particular example I've shown here, they're forming some kind of checkerboard order in the orientations of their spins. This is some antiferromagnetic order formed by these contact interactions in a Fermi-Hubbard model, in this case, of atoms that can hop between sites and interact if they're on the same site. So that's one example of the type of interactions one can realize. One can also have somewhat longer range interactions if you excite atoms to, let's say, Rydberg states. So the electron is in a highly excited state, then atoms can interact over distances of several microns, and then you can have atoms in sort of individual separate traps that talk to each other over a longer range. But still, kind of one of the limitations in most of these systems is that atoms only interact with their neighbors. So interactions quite generally tend to be local and decay with distance. And that actually turns out to be perhaps a problem if you would like to study something where information spreads exponentially quickly over all degrees of freedom. So in particular, this sort of locality of interactions that's very natural to have in these quantum systems tells us that there's some effective kind of a light cone that limits the propagation of information. So this is not the real speed of light, but there's some effective speed of light right in this quantum mechanical system where that's essentially set by the characteristic, let's say, hopping rate of atoms that are trapped in a lattice. If I have just nearest neighbor interactions, information can kind of spread linearly in time. But I won't have information that can spread exponentially quickly over the entire system. This is, by the way, is an actual experiment that was done kind of measuring the so-called Lieb-Robinson bound on the propagation of quantum correlations in a system of atoms in an optical lattice. Okay. And actually, even so, some other systems, like I mentioned Rydberg atoms or also trapped ions, they might have some power law decay of interactions. But even so, in that situation, there's still something light cone-like. It now might have not a linear shape, but some polynomial shape. But this will still prevent you from having sort of exponentially fast spreading of information across all degrees of freedom. So kind of one starting point that we started to think about in my group is, could you build things where one has sort of only a logarithmic time for information to spread from one to many, as would be necessary to realize this black hole-like fast scrambling? And so, we can look at Hamiltonians that have been written down that are understood to behave in this way. One is the Sachdevi Kataya model. Is this something that has been talked about in this summer school? I don't see many faces.
I don't think it's really been mentioned yet. Yeah.
Okay. So just
I'll hear more this week. Yeah.
Yeah, okay. So I'll just briefly say, so, right, and so this is some model where you have fermions that can kind of hop in a completely non-local way. It's some correlated hopping of pairs of fermions. The key thing is it's not something like atoms hopping from nearest neighboring sites in a lattice. It's very non-local. Actually, also some of the earliest proposals thinking about trying to understand this concept of fast scrambling thought about toy models of, for example, billiards on a tree graph. So here things are kind of local, but in a very exotic geometry, right? That doesn't look like sort of a natural thing necessarily to realize in the lab. Okay, so we would like to be able to explore some of these more exotic forms of interaction. The dream would be to have something like a function generator for controlling the graph of interactions in my quantum system. So this, maybe I want some sort of random graph where every atom talks to every other. That would be something like this Sachdevi Kataya model that I wrote down for fast scrambling. Maybe I want something like this tree graph. Okay, so how might you go about doing that? So the general approach that we take in our lab is we have a system where we have some spins encoded in cold atoms, and they can talk to each other with the aid of photons. And the nice thing is that photons travel at the speed of light, which for our purposes in the lab is essentially instantaneous. So every atom can talk to any other atom. And in the simplest case, every atom actually does talk to every other atom. And then the challenge is actually that we've been most recently addressing is how can one start to now break down and program the structure of interactions so that we can explore, for example, how do the dynamics of the quantum system depend on the connectivity of interactions, going beyond the local interactions that are most natural. Okay, so I gave you a little bit of kind of motivation and background. And now I'm going to say a little bit more about how one actually kind of engineers these, let's say, first of all, any atom can talk to any other, these kind of weird non-local interactions, but then also how one can start to program the structure of the interactions to realize things inspired by actually this tree graph I showed you, which I'll say more about later, and how this gives rise to actually some sort of new geometries that are distinct from the physical geometry of atoms in the lab, and even some concept of an emergent geometry that we can probe. Okay, so that's where we're headed. Let's start by drawing sort of some inspiration from this model I showed you before. Could we build things where particles can hop in a very non-local fashion? We can't do that with massive particles, but what we can do in our lab is actually have spin excitations that can hop in a way that is completely non-local, okay? So the basic idea is I would like to, again, have sort of any, so I can think of a spin that can be either up or down as a particle on the site or no particle on the site, right? So the excitation is my particle. And what we'll do is have something where the excitations can hop in a way that is mediated by light. I can convert an excitation into a photon into an excitation that's somewhere else. So to be very concrete, I can think of each atom. Again, if it's a spin half atom, it'll have, I'll think of spin up as having an excitation on this site. I'll convert that into a photon and back into an excitation on another atom. Now, the challenge, of course, is I don't want the photons to just fly off in random directions. I want the photon with high probability to be absorbed by another atom. And the way that we achieve that is actually by putting two mirrors around the system to form what's called an optical resonator. And because the light can take many bounces back and forth between these mirrors, the sort of amplitude for a photon to be reabsorbed, to sort of be scattered into this mode between the two mirrors and reabsorbed by another atom is enhanced by constructive interference compared to sort of the bad process of a photon leaving. So this is the general idea of sort of using strong coupling between atoms and light to realize interactions mediated by light. And I'll just mention actually that this general concept is actually applied in a range of different physical platforms. So for example, microwave photons are used to mediate interactions between superconducting qubits. One can have solid state spins that talk to each other via optical photons. That has some applications in quantum communications technology. And then this type of system I'll talk about is one where we have these cold atoms that can talk to each other with light. And depending on your application, you might choose a different platform. But one of the kind of key features of this cold atom platform is it's again very scalable. So you could have two atoms that have a photon-mediated quantum gate, or you could have an ensemble of 100,000 atoms and use these interactions to generate sort of collective entanglement in these larger systems. So just to give a flavor of kind of some things that have been done in the past with these systems, I gave this example earlier of making quantum states that are useful for enhanced sensing. And so those photon-mediated interactions you can use to sort of have efficiently let every atom talk to each other in such a way as to make a quantum state where if one spin is pointing up, another spin is more likely to be pointing down, and that reduces quantum fluctuations in the number of spins up and down in a way that gives you some squeezes the quantum noise, and this has been used, for example, to make more precise atomic clocks. So that's kind of one direction that this toolbox is used. On the simulation side, there have been a number of different directions also explored with atoms in talking to each other via photons. Some inspired by condensed matter, like realizing actually super solid phases. But what I want to talk about is sort of taking this toolbox and moving it to where we can explore some ideas from quantum gravity. And so, okay, so the first thing that we're going to want, yeah, I see someone unmuting himself.
Can I ask a question?
Yeah.
I was wondering, this method you described, I guess principle can be applied to the SYK model as well, where you just Like, but the problem is, how do you control the Q in the SYK model in that case, such that you have, say, fixed number of atoms lose a photon and the same number of atoms gain a photon at each time step, or something like that, in order to obtain the, say, a model where you have two atoms dropping and two atoms.
Yeah, so you're saying, how do I get this thing where I have pairs and not just like a single atom? Yeah, so that is not obvious, I'll say. I think in principle, you could arrange something where the process is only resonant for pairs of atoms. But the challenge is it's almost like that's a higher order process in perturbation theory. And so in practice, whenever, I haven't thought about it very long and hard, but it looks like it is potentially difficult to be in a regime where you have those be the dominant processes and things are very coherent. So what I would say about this is, from my perspective, the goal isn't necessarily just realize a model like SYK that has that's already kind of solvable, but maybe to ask sort of, can we learn something by realizing models that are similar in flavor and simulating them in the lab? Now, maybe one can think cleverly about the engineering and really realize SYK. But in some sense, I would say this is more kind of drawing inspiration and asking what other models can we realize that might have some similar physics. And one particular thing I'll just mention right now, because you reminded me of it, is that there are different types of questions you might want to ask. So one is studying thermal states at low temperature. And another one might be asking questions about dynamics. So there are questions about, as a function of temperature, how long does it take for the system to scramble? But also just this question of, is the time linear or logarithmic in the system size? So the second one you can ask even sort of in the dynamics at infinite temperature or at high energy density. And there the details of the structure of interactions matters a lot, but I think the details of does one have these pairs interacting or something simpler are less important. They're very important for the low temperature behavior. Does that sound sensible to you?
Yes, it does.
Yeah.
Just to comment about the SYK specifically, has there been any attempt to simulate it? And the reason why I ask is because it's really solvable at large n, and it can be simulated classically at small n, but like in the region of the middle, that might still be interesting for quantum gravity, and we don't know really what's the dual of the SYK model if you don't look only at high energies. Sorry, at low energies, where is JT gravity, but we don't know what's the completion of the theory. So it'd be interesting to study that model in that transition, let's say, a regime of medium energies. So I wanted to know if there was any experiment trying to reproduce this SYK model using these methods.
Yeah, so there are definitely proposals for doing this in actually a variety of systems, but for example, in condensed matter systems. So actually earlier I showed some picture of something that looked like graphene, and there are some proposals there for simulating SYK, which I'll maybe briefly actually touch on next time, because I want to give a flavor of, what are the different platforms people are thinking about. So so there are ideas there. Great. Okay, other questions at this point?
So I guess I'm curious, like you mentioned trying to couple like non-locally, like I know that in like these like commercial quantum computing platforms like D-Wave or whatever, like there's definitely like locality constraints like going on there. Like, do you also see that in this situation, or is it just like much more sophisticated, and like how hard it is, I guess, to have control like in a certain area versus like a larger radius?
So in D-Wave, they typically have, like, they kind of fabricate some chip that has a certain structure of couplings, and I think they can turn those couplings on or off, but not all possible couplings are there. We, so far, and to some extent you'll see over the course of the talk how much control we do or don't have, but we don't have arbitrary control in our system of kind of, of all n squared possible couplings. But I'll kind of show you how we're moving into a place where we have pretty sophisticated control, and then maybe we can come back to the question at the end. So I would say the level of control we have is different from what we have in D-Wave, and the basic concept is control it optically and dynamically even, as opposed to fabricate a device with a certain architecture.
Thank you.
Mm-hmm. Great. Okay. So yeah, okay. So first thing, in order to have kind of some degree of optical control over these interactions, I gave kind of a cartoon picture earlier where an atom emits a photon and that gets absorbed by another atom. To be a little bit more specific, the way that we do this, so we have kind of our spins are encoded in some ground states of our atoms, and then there's an excited state, so essentially we have a 2-photon process. There's a laser that couples us to an excited state, and then we're far detuned from the excited state. But the key point is this laser controls basically the coupling of atoms to the cavity. So if we turn on this control field, then we have a process where one atom can absorb a photon from the laser, emit it into the cavity, another atom absorbs it and flips its spin in turn. So key point here is there's a drive laser that basically can turn on the interaction. Now, sort of the setup where we do this, just to give you really a picture, it looks something like this. There's basically 2 mirrors 5 centimeters apart. There's a standing wave of light between these 2 mirrors in which the atoms are trapped. And so spatially, these atoms are pinned. And the dynamics will be going on just in their internal states. And in the first experiments I'll show you, we just have kind of sort of 0.5 millimeter long cloud of atoms. We're not looking at these atoms individually, but again, they're kind of spatially pinned. And we're going to ask we're going to sort of take some pictures of what the spin excitations do in this system. So just as a simple example, here's an experiment where, so each row in this image is some image of the sort of density of spin excitations in our atomic cloud versus position along the cavity. The vertical direction is time. So this is an experiment where at t equals 0, we flipped some spins up and then turned on the light that generates the interactions. And what you see is that these spin excitations that were originally in region A kind of hop over to region B and hop back. There's some oscillations, which indicate some quantum coherence in the system. And the key thing that I kind of like about this image is it was kind of our first way of really seeing directly the kind of non-local character of these interactions. That, in fact, the excitations don't just sort of travel outward from A, they suddenly show up at B. Why do they suddenly show up here? That's something that it turns out you can understand if you say that in this particular case, the strength of interaction between any 2 atoms is just given by the local intensity of the light field. And in this particular experiment, that intensity happened to be strongest toward the left part of the image. That's the center of the cavity. And that's why the excitation suddenly showed up here. Okay, so that's just starting to show that we can kind of see this non-local hopping of the spin excitations. And again, in this particular case, so far, I kind of said this in words, the strength of the interaction between any pair of atoms is a product of local couplings to the light field. So this is not sort of arbitrary control over all of the Jij couplings as you might want if you want like a truly random graph, let's say. It still actually is expected to have a fairly rich phase diagram, including places where the system is chaotic, places where it's integrable, but it's expected only to thermalize slowly and not be a fast scrambler. So kind of the question we'd like to start to get to is kind of, how, if we can start to have more control over the structure of interactions, first of all, how do we do that? And then can we use that to explore how that influences something about how quantum correlations spread in the system? Okay, so before we get to that, I just want to give you a sense of how we're going to kind of see some signatures of quantum correlations or sort of probe the kind of the quantum dynamics of this system. And so our basic tool going forward is going to take advantage of the fact, I ignored this for now, but actually each of the atoms in our system is a spin 1. I kind of pretended earlier it was spin half. It didn't matter for what I showed you before. But each of the atoms is a spin 1. And we typically initiate this system in a situation where all of the atoms are in the m equals 0 state of this spin 1 system. Sorry, in what I'll show you in a moment, we will initiate the atoms all in the m equals 0 state. And this allows, if you have this type of F plus F minus interaction, so earlier I described it as kind of a flip-flop between spin half atoms, but we can have these 2 0 atoms and convert them into a pair of a +1 and a -1 atom, right? So what does that look like? So here's an experiment where we did actually just 100 repetitions of the same experiment. Each time we initiate the atoms in the 0 state, we turn on interactions, and we watch after some time how many atoms are in the +1 and the -1 state. We just take a picture individually of the atoms in each of the 3 states. Okay, and what you'll see is that, first of all, there are large fluctuations from shot to shot. Sometimes you see population in the ±1 states. Sometimes you see less, but it's always correlated. And so what's going on here? So we see these large fluctuations, but they're always correlated. So this is actually something that one can understand quite well. If I wanted to sort of write down a Hamiltonian for this, I would describe these three internal states as three bosonic modes that I'll call A, B, and C. We start with all atoms in the C mode, but you can take two C atoms and turn them into an A and a B atom. And I'm just going to briefly say the algebra isn't super important, but you can transform this to coordinates where this basically looks like two decoupled harmonic oscillators, both of which are negative mass or unstable. And so there's basically an instability to kind of forming these correlated pairs of atoms in the A and the B state, or the +1 and -1 state of this spin 1 system. Somewhat intriguingly, it turns out the dynamics of this in principle give rise to something that looks like where each state alone, the A state and the B state, the number of excitations should look like the thermal distribution of a harmonic oscillator, but it's coherent dynamics, and the system as a whole is a pure state. So this, some of you may have heard of. This is kind of what I've heard called a thermofield double state. And I don't know whether that's just a random coincidence that it makes that type of state, or whether it's interesting for simulations of quantum gravity. But okay, that's kind of a side note. This prepares some kind of an entangled state, and that shows up in these. There are large fluctuations in the populations of these two states, 1 and -1, but they're correlated. Okay. This is just kind of to illustrate the instability. The population in these + and -1 states takes off exponentially. This is actually a phenomenon that has been studied in other physical systems, notably by collisional interactions that create these correlated pairs in Bose-Einstein condensates. It's also a little bit like creating correlated photon pairs. But the neat thing that we're going to try to do with it is ask, can we use control, optical control, over the structure of the interactions? Well, one direction would be to sort of generate some designer entangled states, but this is also going to give us kind of a means of probing the structure of interactions mediated by the cavity. And when I've showed you what I've showed you so far, the structure was all to all. Every atom talked to every other, and the correlations extended across the entire cloud. Okay? So we want to take this a step further to having a higher degree of control over the interactions. First, let me just pause and ask whether there are any questions about this kind of pair creation physics I just showed, because we're going to use it now to probe the system. Okay, I don't immediately see hands up. Are there?
Sure, I'll ask one. So I guess sorry, did you mention that scrambling was dependent on like the graph, or like the way you actually like arrange the atoms, like, yeah, so I guess like I'm curious, what was the dependence, and like how did you like decide what sort of arrangements to use?
Okay, so I'm actually going to come to that. So next I'm going to show you how we can control a little bit more the graph of interactions, and then sort of how we might want to control it to enable fast scrambling. Okay, so yes, okay. So in order to sort of more cleanly now start to ask about the structure of the interactions, the next thing we did is say, let's make this system a little bit cleaner. Let's work with an array of, in our case, atomic ensembles. We actually get some benefit in the interaction strength that's collectively enhanced if we have many atoms per site. So that's the situation we'll be working with. But our goal is going to be, ultimately maybe arbitrary control of the couplings, but to start with, arbitrary control over translation invariant couplings. So can we control the couplings as a function of distance in this system? And if once you can do that, it's also easy to do things like maybe add disorder if you want, right, to make things richer. But we'll try to control the couplings versus distance. So the basic idea for how we do this is that first we actually turn off the long-range part of the interactions by adding a magnetic field gradient, right? So the interaction is this: you have two zero atoms and they turn into a +1 -1 pair. If I have a magnetic field gradient, then that process is off resonant if the atoms are far apart, and it will only be resonant if the atoms are on the same site, okay? And so in the presence of a magnetic field gradient, if I measure like correlations, let's say, between the number of +1 atoms on site I and the number of -1 atoms on site J, I'll see correlations only on the diagonal, right? these pairs can only form sort of on site. So that's what we see. That means we've now sort of turned off the long range part of the interaction. And now what we're going to do is controllably reintroduce it at some distance that we get to pick. And the way that we do that is by adding, we had a control field that drives these interactions, but now we're actually going to send in 2 frequencies. And so the idea is by absorbing a photon of one frequency and emitting a photon of another, we can bridge the energy cost of creating a pair at a certain separation. So now when we measure correlations between +1 atoms and -1 atoms, you'll see that there are correlations on the diagonal, but also at some distance that we can set by this frequency difference in our laser field spectrum. Okay, so we can turn on interactions at a specified distance. So here's a plot where the horizontal axis, each row is showing correlations versus distance. I've sort of taken that 2-dimensional plot and collapsed it to say just what is the correlation between population of +1 atoms on a given site and population of -1 atoms a specified distance away. And the vertical axis is the frequency with which we modulate our laser. And you can see that just by changing that frequency, the distance at which we observe these correlations tracks. So that gives us a knob now for controlling the graph of interactions. It's actually very precise control, so you can decide, do I have interactions at 10 sites, 11 sites, 12 sites? And now it's actually very easy to control the spectrum of a laser field. So the idea is now if I generalize this and I drive with multiple frequencies, then I should be able to have kind of arbitrary patterns of these couplings, J of I minus J. Okay. So maybe just before we go into making more complex patterns of couplings, I'm just going to briefly give you one other way that I like to think about this. So I said before the frequency spacing between kind of 2 teeth in my control field sets the distance at which I have interactions. Or sometimes I like to think about this, I can Fourier transform this and say the modulation waveform in time actually sets the energy, the dispersion relation, so sort of the energy versus momentum. So this is sort of a complementary way of thinking about this. And I can, so either think of things in the frequency domain and in real space, or in the time domain and in momentum space. And so, but one of the nice things we can look at, for example, is if I turn on interactions, let's say at a distance of 3 sites, and measure versus time, you can see kind of correlations spreading from to sort of 3rd neighbors, 6th neighbors, 9th neighbors as a function of time. Or equivalently, you can see a peak in momentum space that corresponds to this periodicity that grows as a function of time. And that peak actually corresponds to a particular peak in the modulation waveform. Okay, so anyway, so this is a way of controlling either the graph of interactions or equivalently the dispersion relation for these spin excitations. And now, one of the sort of insights that kind of came to us from thinking about the fact that this modulation waveform sets the dispersion relation is I have a finite size system. And so there are actually only sort of discrete points in momentum space where the dispersion relation is defined. So, sorry, there we go. Now the slide matches what I'm saying. And so it turns out that really maybe you should think about pulsing this waveform at discrete times. Okay, if you do that, it turns out you can even realize a system with periodic boundary conditions. So you've precisely realized then actually the dispersion relation for a spin chain with periodic boundary conditions if you pulse this waveform. That shows up in the fact that I have correlations at some distance d, but also at the length of the site, the length of the chain minus d. And now, okay, so we can control the distance at which interactions are there. We can turn on periodic boundary conditions in the system. This starts to already show you that you can kind of realize, graphs that are different from kind of just the physical geometry of the atoms. And in fact, so this is some example where effectively the geometry of the system is something like a ring. I can try and argue that from these correlations, but my students said, I wonder whether we can directly kind of reconstruct the geometry of the interaction graph from the measured spin correlations. So here's an experiment where, again, so we, let's say, drive with nearest neighbor interactions, but we play this trick that gives us periodic boundary conditions. And then from the measured correlations, we said, let's adopt some ansatz for these correlations decaying with distance. Turns out that in our system, a sort of natural ansatz is that the decay is a Gaussian. But the idea is, let's say they decay with distance in some effective geometry, which we would like to identify. And so you can ask, what is sort of the best fit embedding of these sites in 3 dimensions to explain the structure of the correlations in this system under this ansatz that they decay with distance. And what one sees is that the best fit geometry is actually, in fact, a ring. Okay, so this is really just taking the data and asking what are the coordinates that best explain the correlations. We see a ring, and we've actually drawn in here every possible bond between pairs of sites. So in particular, there are n squared possible bonds, but if the correlations are weak, then the bond has a very low opacity and you don't see it. So what you really see is the ring that pops out. Okay, so that starts to show that we can kind of realize some graphs that are different from the geometry in the lab. You can start to kind of explore, what other kinds of graphs can I make? So here's an example where we turned on interactions at third neighbor sites, open boundary conditions. We measure the spin correlations. So actually, here's a quiz. What do you think will pop out if I ask what is the best fit geometry of the sites in 3 dimensions to explain these correlations? Anyone? I can give away the answer for this one, but then you're going to have to guess for the next one.
Is it 3 disjoint rings or lines?
Yeah, exactly. So here I didn't do periodic boundary conditions, so you're exactly right. It's 3 disjoint lines. Yeah, and so that's just what pops out of this reconstruction. We can be, and that makes sense. I could have drawn the graph like this. We can be fancier and say, let's turn on interactions for nearest neighbors, periodic boundary conditions, and let's also connect opposite ends of the ring. In this case, I'll do ferromagnetic interactions between nearest neighbor sites, anti-ferromagnetic interactions across the ring, and just for fun, because we can do that, it's just the phase of our modulation waveform dictates is it ferromagnetic or anti-ferromagnetic. Okay, we measure some correlations. Any thoughts what will pop out from this one? Nope. Okay. Okay, so this one actually is a Mobius strip. So that's kind of fun. I think this starts to kind of illustrate that, we can make graphs that are very different from what one has in the lab. We can kind of play with, different drive waveforms and, reconstruct these different geometries, a cylinder, a Mobius strip. We can control whether the interactions change sign with distance or are all anti-ferromagnetic. Okay, so there are lots of things you can do with this. Making exotic geometries, studying non-trivial topologies. Actually, these interactions that change sign with distance are of interest for studies of spin glasses. But sort of some of these things you can also do in other platforms. So there are other systems where you could make, let's say a triangular lattice. We can make that, but you can also make that by physically positioning atoms or polaritons. So one of the things that, again, the motivation was, can we make some of these exotic things that you can't do by other methods? And so that's what I want to get to next. Now I'm worrying because I think we spent more time than I expected in the breakout. And so so I don't want to rush through the fun quantum gravity part of this. So what I'm actually going to do now is pause and ask whether there are questions. And then next time we're going to get to, at the start of next time, we'll get into how can you use this toolbox to make something where I don't just sort of control the graph and generate some program in some geometry, but where there's some sense of an emergent geometry with something that we can maybe think of as this extra dimension. Okay?
Okay, that's great.
You're unmuted. Yeah.
Yeah. I was just going to give you a 5-minute warning, but I think this is a good, if this is a good time to stop, then we can see, if there are questions.
Yeah. Are there questions at this point?
Yeah, I have a question. So, it's regarding the Mobius strip geometry. So, can you go back to the previous slide?
This one?
I just wonder. Yeah, that one. I just wonder, what makes it the resulting surface non-orientable. how do I see this from the coupling?
Yeah, so basically like, so in the sort of first way I drew the graph at the top, so one thing that can help orient you is that nearest neighbor bonds in the physical geometry are ferromagnetic, and just by choice, that's what we decided to do. And across the ring, they're anti-ferromagnetic. And now if I look at kind of this reconstructed 3D geometry, if you look closely, you might not be able to see it. The sites are actually numbered. So I'm just going to show you. This is like site 0 in my physical geometry. And then as I wrap around, right, I just follow this single red edge. That's going once around this kind of wheel that I've drawn here. And then these blue bonds, these are the ones that in the kind of wheel schematic, right, are opposite a distance of 9 sites in the chain of 18. The fact that it kind of has this twist, that is related to basically just the kind of the number of sites that we've chosen. But you can kind of, right, so you go sort of, as you go once around the ring, you go once around the edge of the strip. You can make a different graph like some of the ones I showed on the next slide where it's a cylinder and it doesn't have the twist. So I don't know, does that answer the question or?
Yeah, it does.
Okay, great. Yeah.
So what's the, this is the follow-up. So what is the significance of like putting ferromagnetic or anti-ferromagnetic coupling between the sides?
Yeah, so in this case, like, so one question you can ask is what are the implications for sort of the physics that you see? So in this case, actually, the fact, so you can sort of ask what is kind of the spin texture that the ground state would have in this. If I think of this as kind of let's say a classical XY type model, which in some approximation, because we have many atoms per site, that gives us some intuition for how to think about it. So basically that means sort of for neighboring sites, the spins are almost aligned, and across this wheel, they're anti-aligned. And that actually what we measure is consistent with that. And maybe I didn't emphasize it, but the colors of the bonds here are the signs of the correlations. It's not actually immediately obvious in this dynamical experiment why we should create anything that's near the ground state. But this is actually a feature of this pair creation process, that it sort of amplifies actually kind of low energy, it amplifies low energy momentum modes that are at low energy. This is kind of a feature of this pair creation process. Okay, so for us right now, I think it's just been a nice, I would say we're kind of characterizing what we can do in terms of control of the interactions. In the broad context of quantum simulation, one question is actually, can you use this to realize frustrated systems that actually map to some hard optimization problems? And being able to have anti-ferromagnetic or sign changing interactions can actually play a role there. So there's actually one direction, which is, can you actually harness this process in kind of computations? So there's a range of kind of optimization problems that can be mapped to energy minimization and spin systems. And so sort of aside from the quantum gravity direction, that's something we're really interested in exploring here. Specifically, there are models for the physics of spin glasses that rely on having sign changing interactions. And so this would actually be an interesting direction, is to realize those models and probe those systems. So.
I have a question.
Yeah.
Are there residual interactions on the actual lattice scale that are somehow non-local on this new lattice, or they're just negligible?
Can you repeat it? Residual interactions on the actual?
Yeah, you start out with a lattice, and there might be some short distance interactions that you're not controlling. I don't know. Mm-hmm. Are they?
So you're asking about direct interactions between the atoms on this lattice. Mm-hmm. It's a good question. So and I mentioned actually this pair creation process has been studied by collisional interactions in Bose-Einstein condensates. If we wait for a very long time, we can actually see some of that collisional pair creation. The sort of characteristic time scale is probably like hundreds of milliseconds for that, whereas the process we're interested in happens kind of on a typically like sub-millisecond time scale, so there's a pretty good separation of scales.
Okay.
Yeah, it's a good question though. Casey?
Yeah, actually I had 2 questions. So one of them was, so could you, or maybe you've already done this, I don't know. Could you do this in such a way that you end up kind of triangulating the surface of a sphere?
Yeah, so I think in principle you could do that. The biggest challenge for us probably has to do with sort of how many sites do you need to have a reasonable approximation to the surface of a sphere.
Right.
In general, sort of by adding interactions and another like non-commensurate distance, you can sort of make effectively another dimension. Although I guess the sphere is kind of, I have to think about whether I probably would have to make something that's effectively 3D and only fill the sites, only fill certain sites, I think. Maybe you can do it with periodic boundary conditions and I'd have to think about that. So I think the biggest limitation is like if I want to make a buckyball or something, right?
Yeah, sure.
I haven't thought carefully about whether you could do that, but I would need 60 sites. Right now, the most we've worked with is about 20. I think order 100 is possible in principle within the confines of sort of how large is the strongly coupled region of the cavity. So not totally crazy. If you come up with a coupling pattern that will give me a sphere, let me know because that would be fun.
Sure. Yeah, it's just really interesting. So I have another question. So, so you're kind of showing, or you're showing that you can make these geometries out of these kind of the interactions, these couplings of these different sites. And I was wondering if you could realize, and this might be going into what you're going to talk about later, if you could realize some type of a horizon in these geometries, where say the interactions, or if you were to start with some pattern of entanglement or some interaction behind the horizon, it doesn't talk to the others outside of the horizon on your little geometry that you created.
That's a really interesting question. I don't have an immediate idea for how you would do that. Maybe you do.
I don't.
In which case it would be interesting to talk. But maybe, maybe once I say a little bit more about what we're doing next time, if you have ideas, I'd be happy to hear them.
Sure.
Yeah. Yeah.
Thank you.
I think this idea of the horizon might also rely on having some kind of like emergent bulk geometry. And so I'll say kind of what we're doing in that direction next time.
Okay. Great.
Yeah.
Thank you.
Okay. So are there other immediate questions? If not,
questions. All right. If not, let's thank Monika for the nice lecture.
Yeah, and so I'll just say next time I'll finish talking about this idea of emergent geometry in this cold atom experiment, and then get into kind of fast scrambling and also how are people measuring that in some other systems. So
okay, great.
Yeah.
One thing that we'd be doing. Usually the recording stops at some point, and then there might be further questions if you have time to hang out.
Okay, yeah, I can hang out for a few more minutes if there are further questions.
We can just see, but we'll probably have the recording stop.
Sounds great.
Great.